Now, one could argue that it's not that surprising that when you start off with a normal distribution, this bell-shaped original data distribution, that the sampling mean distribution is also approximately normal, which we can see. But the central limit theorem, the power of it, tells us that the original data distribution does not have to be normal, not even close to it. That as long as you sample plenty, that you sample often enough, these two sampling distributions will turn out to be bell-shaped, normal, even for very non-normal population distributions. So let's give this a try. Go from a normal to, let's say, a skewed. Very typical in financial data or housing prices. You have a fat right tail. The median is to the left of the mean. And if you sample just a few times, the sampling distribution of the sample mean will look nothing like a normal distribution. You can see this one resembles your fat-tailed, your skewness of the original distribution. However, the central limit theorem has to hold here as well. So if we repeat the sampling, let's say 1,000 times, you can see that the sampling distribution shape again is close to a normal. If we now repeated the numbers from before, if you divide 6.22 divided by square root of 20, you should end up with a number that is close to 1.34, and the same for square root of 10. Now we can even build our own custom distribution. So we can start with a bimodal. See how you can build your own distribution here. A bimodal distribution is, to me, probably the most non-normal distribution you can imagine. So what if there's a cluster of data points here and a larger cluster over there? Let's see this and that. Yeah. Now you might wonder, how in the world could we end up with a unimodal bell-shaped normal distribution in the sample means? And the point is that we are not trying to approximate the original data distribution. We are only concerned with how the sample mean varies around its mean. And if you repeat this plenty of times, you can see that here in the sample data you are still in a bimodal picture. Yeah, that will never change. The central limit theorem does not say anything about this distribution becoming normal. Far from it. It remains what it is. However, now if we repeat this plenty of times, you can see, and the lower one approximates the normal faster than the upper one because of its higher sample size. Again, we are at the normal distribution for an arbitrary distribution up here. Let's try the last with the uniform. The animation is here. It doesn't decay. It's a uniform distribution, and yet the sample mean will, of course, be approximately in the middle of the data, which is where the mean is. The mean is 16, and the shape of it is exactly like what we saw before.